you hear me? My name is Julian Martinez, Senior Developer Advocate, and I'm super excited to get today's session kicked off, where we will be learning the ins and outs of Rust smart contract development. So I'll go ahead and kick it off with a quick introduction. Again, my name is Julian Martinez, Senior Developer Advocate and Common Man here at the Stellar Development Foundation. Once again, over the next, half an hour to an hour or so, depending on how you guys are feeling, we're going to dive into some basic smart contract development, and we may even scale it up to maybe getting into a staking smart contract. Just kind of depends on how the flow goes. All right, so first things first, we're going to go ahead and dive into a great online IDE tool here. It's called Okashi. Again, Okashi is an online IDE. It's really good for iterating on your smart contract ideas. It's got a cool code window where you can type in all your syntax. There's the contract window where you can actually call the functions related to the smart contract that you just coded. There's also a console window here that shows the output of the smart contract calls, or the function calls rather. So if you'd like to follow along, you can actually scan this QR code. And as I'm updating the smart contract online, you should be able to see the smart contract being updated on your local machine as well. So what I'm going to do here is bring Okashi to my main screen. You should be able to see it here. All right, so this is Okashi. Again, we have the code window ready for all the syntax, and this is where the bulk of your logic will live for your smart contracts. We have the contract window, which is going to hold all the functions, and it will allow you to execute and invoke different functions that live on that contract. And you have your console window here, which is just going to output it's going to show the return data of the function call itself. All right, so let's go ahead and dive into Rust in Sorbonne. If you don't already know, Sorbonne is Stellar's smart contract platform. So a few things here. First things first, you see the flag no SCD. That is to tell the compiler to not use Rust standard library. Sorbonne smart contracts use this flag and optimize for smaller contracts, so they don't take up as much space on the ledger. This makes for good forward term thinking for things like state bloat, and overall just being mindful of not taking up more space and storage than you need to, because in the future it can lead to bottlenecks and user experience, and overall just becomes unmanageable. So you see here on line 3, use Sorbonne SDK. This is because Sorbonne uses a special dialect of Rust with dedicated data types and some special attributes. So we're importing a couple of attributes here, namely contract implementation, the env data type, symbol, string, and symbol short. Now let's go ahead and cover a few of these. These two attributes are mainly pertain to telling the compiler to treat all the following syntax as a contract would be treated. So when it comes to the contract implementation, it exposes all the publicly facing functions to the environment for processing through different mechanisms like testing, static function testing, etc. So with env, this data type is going to be responsible for accessing smart contract storage within the contract itself, as well as data from the ledger. So you'll see how we use this a little bit later when we're creating a key value, kind of like storage mechanism for the smart contract. Symbol. Now, symbol is I don't want to say it's another term for string, but you can think of it as a string. So there are two types of symbols. Short symbol, which is a string of up to 9 characters, and then long symbol, which is a string of up to 32 characters. But the difference here is that long symbols actually require you to pass in the env data type before constructing them. Here on the next data type, we have the string. String is exactly what it sounds like. Here it's going to be a concatenation of letters. Symbol short is a function that we use to kind of just quickly create short symbols. In this case, we're going to create a short symbol for the word title. Now you see here on line 5, const title symbol equals symbol short title. We're just going to use this as kind of like a label for the key value system that we are about to set up. So again, you see const title, symbol equals symbol short, and then we're using the word title. All right. Here on line 7, you see the contract attribute followed by line 8, pub struct title contract. So we're creating an empty struct, and all Sorbonne smart contracts will follow a similar pattern. You see a contract attribute, the empty struct with the name of the contract itself, and then followed by a contract implementation attribute, and then the implementation of the actual contract. So let's go ahead and start writing some functions here. This is our title contract, and the main purpose of this is to kind of illustrate the key value system when it comes to storage. So I'm going to create a value for a key, and then I'm going to go ahead and, well, I'm going to create the key value getter and setter. So we're going to be able to set a value to a key, then we're going to be able to retrieve that value from a key. So let's go ahead and say pub function. We're going to say set title. This is going to take in 2 arguments. We're going to say end of the type n. We're going to take in a string, and this is going to be for the title value. We're not going to return anything, so we'll go ahead and get right into the logic. Again, referring back to the env data type up here, you see env storage. We have to go instance dot set, and then we're going to actually, if you see set, we're going to say set and title, and then we're going to bring the argument from the title, or bring in the argument title in from the functions here, or the argument here. So let's go ahead and compile this. Let's see if this works. Again, you see env storage. We're taking in the we're accessing the smart contract storage here. We have instance, which is a certain type of data type for Sorbonne smart contracts, of which there are 3: temporary, persistent, and instance. And then you see the set method here, where we're actually setting value to the title key, and then the value will be title. But it looks like we have some errors here. Unused variable signature length, unused variable signature literal, cannot find type title in this scope. Okay, public function, string, title, and storage. Okay, we got some issues here. So let's see what we got. And storage and set title. So this looks like it was compiled. Function set title. All right, I'm just going to go ahead and do a quick sanity check. I do have the correct function on the side here. I'm also wondering if this is going to work. All right, let's go ahead and see what the issue was in the last set title and title. Okay, I'm not sure what the issue was here, but let's go ahead and let's see if we can actually debug it side by side. Let's go ahead and find the difference. Let's see this. Let's see if this compiles. It probably won't. Okay, well, I'm not sure what the issue was here, but long story short, here is the correct function. As you can see, we see pub function set title. We're taking in 2 arguments. One is the data type env. The next is the data type string for our title. We're accessing the smart contract storage again by typing m.storage.instance. Again, there are 3 types of storage in Sorbonne smart contracts, and they each kind of serve a purpose when it comes to how long you want your data to live by default. Again, temporary, instance, and persistent. For this use case, we're just going to use instance. We have the set method here, where we are setting a value to the key title, and the value will be the title argument that we're passing in. So let's go ahead and set a title. We'll say Sorbonne rocks. Cool. It looks like our function call went through, and we didn't get any return data. However, to access this, or to access the data that we just set to the contract storage, we need to create a getter function. So to do this, we actually just have to follow the same structure here, pub function. We have to say get title. We're only passing in one argument, and that is of type env. And we want to return a string. So for this, we're going to go end storage instance, and we're going to say get, and we're going to say and title, and we are going to say dot unwrap, or I'm going to say string from string, and we're going to pass in the end, and we're going to say default message. All right, so default message here. So what is this doing? Let's see if this compiles first. Don't want to hit a block. Okay, instance. So it looks like we got a typo here. All right, so what are we doing in this function? You see pub function get title. So we have one argument that we're returning, or one argument that we're taking in, that's of env, and then we're returning the data type string. So here you see env.storage. Again, this is how we access the contract storage. You see instance, which is the storage type, .get, which is the method to retrieve data, and you see the key title. So we're retrieving the value that lives at the key title, and to access this value, you see .unwrap. And now usually this would be fine, right? But if no value lives at that key, then you need to have some error. You need to have some like error handling, right? So if there is no value that lives at this key, we're just going to return a default message in the form of this string that we defined. So let's go ahead and get the title. All right, so this is a new deployment inside of a contained web browser, inside of a contained web app. So technically, I have not set any data to this new deployment after creating this function. So I click get title, the default message will be returned, right? So get title, default message. I'll go ahead and set a new title. We'll say stellar rules. All right, so we set a new title. Instead of Sorbonne rules, we'll say stellar rules. We'll go ahead and get that. All right, cool. So now you see that we are able to set some data with the set title, right? And then we can get the data by retrieving it using the get title method. Now, once again, this was Okashi, which is an online ID for Sorbonne smart contracts. Now, what I'd like to do is actually the kind of tutorial over to the CLI part of things, and we'll actually start coding and deploying on testnet, which you can actually do on Okashi as well. But I do want to get you guys familiar with the tools that the SDF offers, mainly because when it comes to the Stellar CLI, this will be one of your best friends one of your best friends along your Stellar smart contract development journeys. So let's go ahead and switch the windows here. All right, I'll close this out for now. All right, so getting started with the Stellar CLI and Rust on your local machine takes 3 easy steps, right? So what you're going to want to do to make this easier for yourself is to actually scan this QR code here at the bottom left. This will take you right to the getting started section of the docs, where you will be able to find these exact commands. You'll put them right into your CLI. But for the sake of the tutorial, I might as well kind of go through the steps with you guys. So we see curl proto HTTPS TSLV 1.2 SF HTTPS, and we're gonna say rust up sh.sh. So what this is going to do, TSLV TLSV. HTTPS RS. Okay, so what this is going to do is install the Rust toolchain on your computer. I've actually done this already, so you can see I have Rust version 1.79. It takes a little while, so I will kind of spare you guys on moving forward so fast because I know it takes about 2.5 minutes. So in the meantime, I can kind of go through the installment process for the rest of the tools. We say rust up and target add wasm, oh my gosh, 32 unknown the demo effect unknown. All right, so what this is going to do is tell the Rust compiler to compile Rust smart contracts into wasm, and it's going to output those files into a target directory. We'll see this process a little bit later, but yeah, so that's what the second command does, is tells the Rust compiler to compile Rust files into wasm. And the last command, we have cargo install, and we have locked stellar CLI. So this is going to install stellar CLI, the latest version. So we're on version 21.2.0. And I know, again, this would probably take around 2.5 minutes. So if you're following along and it takes a little while, not to worry. I'll move slow throughout the rest of the tutorial. So just to kind of like make sure we have the correct version of Stellar installed, we'll say stellar-v. Again, you see Stellar 21.2.0. Cool. So what we'll do next is we'll actually go here and we're going to say Stellar contract. Actually, we'll say Stellar and then we'll take a look at all the methods that you see. You see the commands here: completion, contract, events, keys, XDR, network, etc. So let's go ahead and dive into contract. We'll go ahead and clear this out. We'll say stellar contract, and then we'll say init, and we want hello world. So hello and world. All right, so you see the messages here, writing hello world, etc. All these files being written, and you see it has injected a cargo or a Rust project right into the directory that we were working from. And let's go ahead and click into our cargo toml file. You see a backwards compatible SDK, Sorbonne SDK 20.3.2. This is a local issue, so I'm just going to go ahead and restart my Rust analyzer, see if that fixes this little error. But we're going to go ahead and dive right into the hello world directory. So we'll cd hello world. Cool. And let's take a look at the contract here. And you see an older contract that we were not using, or not an older contract, but you see a boilerplate contract that is different from the one that we're using. However, I'm just going to go ahead and bring the contract that we're using right into here. And we're actually going to work right from this. So you see this here, where we have the Hello World project that we're in. And one cool thing about the Stellar CLI is that you can actually generate key pairs right from the CLI itself. So what we're going to do is exactly that. I'll go ahead and go to Stellar CLI or Stellar keys, and we'll go ahead and list the keys we have already. So Stellar keys ls will list the different key pairs that you have available to actually sign transactions. And what that means is every time you deploy a contract or invoke a function, etc., that takes fees, right? So there has to be a source account assigned to that transaction to pay that fee. Now we have two that exist already, but let's go ahead and demonstrate how to create a new one. and we'll say stellar generate, we'll say stellar keys, generate, and we'll define the network testnet. And we'll give this a name. So for this name, we want it to be Stroopy. So let's go ahead and generate a new key pair called Stroopy for the testnet network. Cool. You see that the function has went through, or the method has been executed. Let's see, ls, right? So you see Stroopy, Alice, and Joe, and we'll see address for Stroopy, and n stellar keys show Stroopy. All right, you see the you see the key pair here. This is the public key and the private key. By the way, I'm just doing this for demonstration purposes only. Please never share your private key with anybody. But here is what happens when you generate a new key pair using the stellar keys generate method. As you can see the address, it begins with G, and the source account, or the source key, that begins with S. So moving forward, let's go ahead and deploy this smart contract to the network. And we're going to go ahead and say stellar contract deploy, and we'll say, actually we have to start with stellar contract build. Stellar contract build. And again, what this is going to do is actually compile the Rust smart contract into its WASM format here, and it'll be in the directory wasm32-unknown-unknown. It'll take a little bit, maybe around 1 to 2 minutes, maybe less. All right, so about 1 minute. We'll go ahead and look at the release directory. You see here, wasm32-unknown-unknown. In the release directory, you have the hello world wasm file. That's because we're actually still defining this project as hello world. So when it gets compiled, you'll see that it gets compiled into the name of the project itself. So to resolve that, we would actually have to go and change the name of this project as a whole. But we won't do all that for the sake of this demo. So we're still working from the hello world directory, and we're going to deploy the stellar smart contract onto testnet. So we'll say contract deploy, right? And we have to define the wasm. Wasm is going to be target wasm release, and we'll say hello world and wasm. And we'll say the network is going to be testnet, and we're going to say source is going to be Stroopy. All right, so this is the command to deploy contracts onto the network. You see stellar contract deploy. You're defining the WASM location, right? Where the location of the WASM file, so the compiled file of the smart contract. You see network is testnet, and then the source is Stroopy. So let's go ahead and send this transaction. Fingers crossed we get a contract ID back. All right, that was very fast. And you see that this begins with the letter C. So let's go ahead and go back to our key pair. Just a quick lesson on how addresses are defined on Stellar. You see G is for the public address, C is for contract addresses, S is for source account, or source keys, or private keys rather. All right, so we've deployed the contract, and here is our ID. Let's go ahead and call some functions on that contract. So let's go ahead and do Stellar. We got to do contract. And for this, we're going to do invoke, and we're going to define the ID here. And we're going to say network. And we're going to say testnet. Source is going to be Stroopy. And then we are going to define our function by doing the following. We're going to say dash dash. We're going to call the function or define the function. And then we're going to define the argument here. So set title takes in one argument for title. And we're going to use quotes, and we're going to say stellar smart contracts That's too long. We'll just say Stellar rocks. Cool. All right, you can see here that there is an unrecognized subcommand. So what does that mean? Basically means that I spelled a command wrong, right? So one cool thing about the error messaging with the CLI is that it'll actually kick back some functions that it thought that you meant. So we see here set title. You can use an underscore or a dash or a hyphen. I'm going to go with the underscore here, and we're going to go ahead and um, we're going to demonstrate calling that function. So we'll say set title, and we have the correct function name, so it should work. It looks like it did. And let's go ahead and get title. All right. So just like that, we've used the Stellar CLI to create a new key pair, deploy a smart contract to the test network, and invoke the functions for that smart contract. And just to do a quick recap, some of the smart contract basics that we learned today were data types, as well as a little bit of the ins and outs of contract storage. So really quickly, I kind of want to recap those. Again, we have contract implementation, which are both attributes specific to Sorbonne, and which is responsible for getting data for the from the smart contract as well as the blockchain. On Stellar, we call it the ledger. You have symbol, which is either a string of up to 9 characters or 32 characters. String, which is the string that you're familiar with. Symbol short, which is a function that helps you create short symbols. So that's a little bit about the data types. And now when it comes to contract storage, we kind of went into some 101 for key values, I guess, structure on Stellar smart contracts. Here you see on line 5, const title symbol equals symbol short. Again, we're just using this line as a placeholder to kind of have an easy reference for a key that we're naming throughout the smart contract. Contract attribute with the blank struct with the title here, and this is basically how all Sorbonne smart contracts look. The contract implementation attribute followed by the implementation of the struct or the contract itself, and the functions here. You see pub fn set title. Again, we're taking in two arguments. The first one, you will always see env as an argument within each function for Sorbonne smart contracts. And this will kind of be like the pattern that you'll see throughout your development journey with Stellar. So just get familiar with this structure altogether. So we have env as the first argument and then title as the next argument, taking in a string value. Again, to access storage within a smart contract, you have to write the syntax env.storage dot and then the type of storage. So in this case, instance, but again, 3 types: temporary, instance, and persistent. To set a value to a key, you call the set method, right? And then you're defining the key. So in this case, title, which is a placeholder, or the title or the name of the key. And then the value that we're setting is the argument that we're passing in for the function, also called title. All right. And then to retrieve that data, you have to go through a similar process, but reverse. So again, accessing the smart contract storage, end.storage.instance, right? .get is the method that you'll be using. You're referencing a key for the key in the smart contract storage. So the key here, title, and to get the value of the key, you have to use the unwrap method. In this case, we're planning for errors, so we're saying unwrap. And if no value lives at that key, then return this default message. All right, so that's a quick recap about on some basic smart contracts. But we do have quite a bit of time left, so I'm gonna go ahead and kind of just like dive into some more advanced smart contract methods, or not methods, a little bit more smart contract, a little bit more advanced smart contract logic. And I'm going to go ahead and just kind of freestyle this, but I do have a staking repo that you guys can reference for your own kind of like studies if you want to. And you could find it here in this QR code. So this will take you to a hackathon repo that I set up that has a couple of directories in it. You'll find a workshop directory, and I think you'll also find a slides directory, but we'll be working from the workshop directory here. You should see staking and data types. So I'll go ahead and give you a quick overview on how data types kind of look and I guess how they're implemented here. So some of the main things that you're going to want to know is like enumeration, right? One thing that we use here kind of when it comes to Stellar smart contract development, we often use enumerations as maps. So what does that mean, right? When you look at a data key of a smart contract, when you look at a data key of a smart contract, you're basically setting a key value system similar to the key value system that we defined earlier. When we go back to, I guess we can go back to this basic smart contract here. Hello world. All right, so you see const title, right? This is the key, and then again, we're setting the value later with the title, right? So key is title, and then the value is also named title. So if we go back to the staking smart contract, right? Go ahead and dive into it. You see here, the data key, we can host many keys, and throughout the smart contract logic, we can define the values for these keys. So we'll actually just dive right into this smart contract over the next 30 minutes. And then by the end of it, you should be able to understand more data types, more ins and outs of smart contract storage. And then we'll kind of like take a look at some more examples of setters and getters, as well as cross contract calls. All right, so go ahead and strap in, stick with me. Thank you so much if you've been with us thus far, and I hope you're learning something. Yeah, so let's go ahead and get it kicked off. Again, at the top, you see no STD. Again, that's to tell the or to tell the compiler not to use Rust standard library when compiling Rust smart contracts or when compiling Sorbonne smart contracts, keeping them optimized, small, so they don't take up so much space on the ledger. Again, on line 3, you see use Sorbonne SDK, some familiar attributes we saw from the last example, contract implementation. Now you see contract type. This is to derive a certain type of what's it called? Certain type of, how do I put this? Object from the Sorbonne SDK and treat it accordingly. So we can dive into the ins and outs after, and I'd be happy to get you more information on how attributes work after the stream. So here you see vec. Vector is an array of concatenatable data. So what does that really mean? It's just an array not specific to types. You can have a vector for integers, you can have a vector for strings, a vector for symbols, etc. Address is just the way that or the data type for Sorbonne smart contract addresses. Bytes n, which is a fixed bytes array or fixed bytes value. You have the end data type, which is again used for accessing data on the blockchain and ledger. And then interval, we're not going to get into this, but vec, again, this is the actual data type. Vec here in lowercase is the function that we use to quickly create vectors. All right, so let's go ahead and dive into the data key enumeration. Here in the comment, it kind of explains everything, but this is used to represent the state variables stored in the smart contract storage. Again, it allows for super easy, convenient access to data within the smart contract. We covered this a little bit earlier, but each one of these keys here has a value that's attached to them. So you see public enumeration data key and a list of all the keys within the contract. You see contributions in parentheses address. So what does this mean? This means contributions is attached to many keys. So all of these keys must hold the data type address, right? So address A, B, C, and D, but all of these addresses are mapped to one value. So basically, this data key will record which address made which contribution, right? Contributors is just going to be a vector of all the addresses that have made contributions. Token is just going to be the address of the token that the contract corresponds with. Shared token is going to be the we're actually going to mint a token from this contract to use as uh, a share token. So we're going to distribute tokens when a user makes a deposit. And here we're actually going to write that into the contract itself. Is active is going to be a Boolean. So if this value is true, certain logic ensues. If this value is false, again, a certain path of logic ensues. Admin is going to be an so this address will have certain capabilities and be able to hold domain over various functions. Initialize is going to be a Boolean that tells the caller whether or not this contract is or is not already initialized. All right. So this is our staking contract, right? And again, you see the contract attribute, empty struct with the name, contract implementation attribute, and let's go ahead and dive into our functions. So this is our initialize function. It takes in three arguments. Again, end, the execution environment of the contract. Admin, pretty obvious, it's the address of the admin. Token wasm hash, this is an interesting one because we'll actually be creating a new token right from the wasm hash itself. And then the token will be the address of the deposit token contract. So the acceptable token for the campaign, for the staking campaign. So the token being deposited must correspond with the address that is set here within the smart contract function during this initialize call. And the token wasm hash, we're actually going to be able to use a wasm hash to access an interface whereby we will be minting a random token or a just generated token, a Sorbonne token, if you will, to people who make deposits to the campaign. All right, so diving in, you see some familiar functions here. All right, so the first thing we're going to do is set the admin address in the storage. So n storage.instance set. Again, as previously covered, end to access the smart contract storage, storage to access the actual part of the smart contract for storage. Instance is the type of storage we're accessing. Set is the method. And just a quick variation from the demonstration before, you see and data key and then admin. Same thing as before when you see the other smart contract here, right? Let's go ahead and open this. Same thing as you see here, end storage instance set and title. Let's go ahead and go back here. End storage set and data key admin. Here it's just defined in this data key, so you're just literally accessing that, and then you're passing in the argument for the admin argument here in the function. All right, so you see let share contract equal token create contract. We're actually able to do this by importing. Do we import the token data type? All right. So there is a module here, mod token, and we're actually importing that, importing this module, this file here, into the main smart contract. And what this will do is import the pre-compiled Sorbonne token contract file and will allow the main smart contract to use the functions that live on this contract. So actually from a compiled WASM file, we're importing that into the main file, into the main smart contract rather. So where were we? I'm getting all ahead of myself here. So that's how we're able to use the token file, the token smart contract, to call the function create contract. So let share token right here, we're going to create a new contract by calling the by calling the create contract method that lives on the token file. And we're going to use the token wasm hash here to create pretty much the token file, the token contract from this compiled wasm hash. And we're going to we're going to call that interface at the token contract that we are setting in the initialize function here. Again, you see token client new. All right, so we're going to create a new token kind of like interface over the share contract. And then again, we're going to call the initialize function. So here, we're going to set the admin as the current contract address. So the staking contract itself, we're going to define the decimal places, and then we're going to define the name, and then we're going to define the symbol. So just a quick recap, what are we doing here? We're going to say, let the share token equal a new token contract, right? So we're going to create a new token contract. Again, token wasm hash, token address. All right, so we've created a new token. We've created a new token. And then on that new token, we're calling the initialize function. And this is what we're initializing that new token with. All right, so moving forward, let's go ahead and see what else is happening. We have end storage instance set. So we're setting the token key with the token smart contract address. And then again, moving forward, we're setting the share token key value as the share contract address. And then we're setting initialize to true. So after this is all said and done, most of the data keys have been defined. You have the token being defined as the actual token address that has been passed in by the user. The share token is defined when the share token is deployed and initialized. Is active hasn't come into play yet. Admin was passed in the initialized function, and then initialized, the value here gets changed at the very end of the initialize sequence. All right, so moving forward, we have start campaign. And what this is going to do is just basically set the is active value to true. The thing here to note is that we're actually making a super cool use of the authorization framework on Stellar. So you see pub function campaign admin address. So admin.require auth. This means that the person making the call must be the same value that is passed in the admin argument. I can't pass in G2 if my address is G1. So this will fail if I'm passing in an address that is not the wallet that I'm calling from. So let current admin equals end storage instant get. So we're defining the current admin, right? So we're saying we're going to get the current admin from the contract storage here by unwrapping the key, the data key admin. And then we're going to say if there is no value that lives there, which it should, right? Because we've just initialized a smart contract, then we're just going to return this current contract address. And we're going to say here, we're going to create an assertion. If the admin does not match, or if the admin address that was passed in for the argument does not match the current admin address value, then we're going to panic and we're going to make this function fail. All right, so if that's all good, then we're going to say end storage instance.set data key is active, right? So once we set that value to true, the campaign has started, and let's go ahead and take a look at what that means, right? So we can go the other way, stop the campaign. Again, same exact logic, except for here at the end, we're setting that value data key is active to false. After this, we can easily check the campaign status, right? Pub function, check campaign status, we're returning a Boolean value. So same as from the demonstration before, mstorage.instance.get with the, I guess, target location, for lack of a better term. And then we're using the unwrap or method. If there's no value that lives at the key is active, we're going to return false by default. All right, so let's go ahead and take a look at the deposit functions and withdrawal functions. I just want to make sure that we are, in fact, using the is active variable. It doesn't look like we are. Okay, actually we are here. All right, so let's go ahead and dive right into it. So what does this function do? This function will actually record a deposit made by a contributor if the staking campaign is active. So it takes in 4 arguments, and as always, going to be the execution environment of the contract contributor, the address of the person making the deposit, the token, the address of the token to deposit, and obviously the amount, so the contribution in tokens. Here you see contributor require auth, meaning that, again, only the wallet making the call is allowed to make the call. I can't call deposit and then pass in another wallet address. It has to be the wallet that I am making the call from, that I am clicking the button with. All right, so let's go ahead and move forward. If the status, okay, let is active equals, and then we're going to define this value as a Boolean value. Then we're going to call the function check campaign status, right? So we get that return value and we define that is active. We're going to say if active is not true, we're going to panic and return this message, campaign is inactive. Long story short, if the campaign is not active, you can't make a deposit. All right, moving forward, we have token client new. All right, so we're gonna put the interface over the token address, right? So in this case, we're using the Sorbonne smart contract address, and then we're putting the interface over, and we're gonna call the transfer method. So we're calling the transfer on the XLM token address, at least according to the test here. And we're going to transfer that over to we're going to transfer that from the contributor, from the wallet making the call, over to the current contract address, so the staking contract. And then we're going to transfer the amount specified in the in the call here. Next, we're going to mint the share token to the contributor. So we have let share token equal get share token. Again, remember in the initialize function, we deployed a new token called share token, and then we recorded the address of that share token to the smart contract storage. So here in this call, get share token, we're able to retrieve the address of the share token. We're creating a new client or interface to lay over the share token, right? We're saying token dot mint, right? So we're telling the share token to mint an amount of share tokens to the contributor. And then here we set the contribution, right? So there's a command in here or a function in the smart contract called set contribution that manages the value for the contributor value manages the value for the contributor key according to the address. So set contribution, we're saying getting the address of the contributor and then setting the amount to that key. All right. And then similarly, if we go to the withdraw function, it works exactly the same, but in reverse. So we say pub function withdraw, contributor address, recipient, and token. So you see contributor require auth. Again, super cool here that you can just use the require auth or the authorization framework right in the smart contract, right from the smart contract SDK to kind of have this dynamic authorization framework for things like managing different calls from addresses. So again, you see contributor dot require auth, meaning that only the wallet making the call can make this call. It can't be another address, right? You must pass in the address that you're using. Is active, again, we're doing a call to a function that exists within the smart contract that returns a true or false value, so Boolean value. If is active does not return true, then the campaign or the withdrawal will be null, right? It will not go through. So again, the campaign must be active to make a withdrawal. We should probably change that. All right, cool. So we're getting a couple values here. So let contribution equals self get user contribution. This is going to return an amount. We'll go ahead and dive into how that comes into play a little bit later. Again, token client new, laying that interface over the token address. So this time it's going to be XLM, at least according to the test. And then we're going to say from this current contract address, from the staking address, we're going to transfer XLM over to the recipient, and the amount will be the contribution amount that is defined here and get user contribution. Next, we're going to go ahead and keep moving forward. let share token equals get share token. So we're returning an address value here. Um, and again, laying that interface over the share token address and calling the burn method. The contributor is going to be the uh, the I guess wallet is going to target, and the amount that it's going to burn is the contribution amount. So again, total contribution being defined here, and then you see the burn happening here. So the address of the contributor burning their entire contribution, and last but not least, you see set contribution. We're going to take in the contributor value or the contributor address and set the value of that key contributions to 0. All right, so that's a quick rundown, and I'd like a couple of cool things that happened during this time. So again, we have our data keys and smart contract storage, right? Data key here, a good place to keep all your keys. All these keys have values. How do you manage these values? Well, you use the set method, right? So that's the contract storage, right? So to set a value to a key, you have to go env storage instance dot set. To get a value from a key, you have to go env storage dot instance dot get. So there's some data types and contract storage action happening there. And then one cool thing that I'd like to point out is the cross contract calls. So when we're looking at the deposit function, one thing that we may have looked over is that we're actually making a cross contract call. So you see token client new. All this is that we're using the token contract, right? We're using this token contract to access functions at another address outside of the staking contract. So token client new, laying the interface over the external address, which is the token address, and then we're calling the transfer function on that token address that is defined by this import here. So that might be a lot for some, but this is a cross-contract call, and it's made super easy by being able to use this contract import function, whereby you can actually import WASM files, so compiled Rust smart contract files, and actually call the functions from these compiled Rust smart contract files on other contracts. And it's all super compact and very, very, I guess, malleable for lack of a better term. All right, so let's go ahead and actually dive into some tests here. I'll just go ahead and quickly go into the staking directory. We'll go ahead and run cargo test. All right, there wasn't very much action here, but we have one huge test for everything that kind of goes over all of the things that we just went over. Let's go ahead and just kind of like dive in here. You see the test contribute. We're letting the end be defined as like a simulated environment, or the end here is just going to be like a default environment being simulated. Here we're saying all authorizations have been accepted, so users are able to call different functions when it comes to the authorization framework that we have used here. It's going to make it easier for us to kind of get around any blocks that may occur. All right, so we're generating a couple of new addresses, some mock addresses, if you will, by using the generate method. So address generate, we're using two, so one for admin, one for user. We're creating a token contract. So token one equals create token contract, right? So create token contract, we won't dive into the ins and outs of this just yet, but essentially it's going to create like a mock token, and we're going to be able to use the functions from the token file, or this token.rs file, on this token contract. So you see we're taking in one argument, which is the address, the admin address, and we're going to return a token client. So we're going to say token client new. We're going to register like a default kind of asset contract available from the SDK, and we're going to set the admin as the admin address. All right, so let's go ahead and keep moving forward. Contract ID equals register contract. we're going to pretty much just like upload the staking contract here using this command. Client, we're going to define a new client, so a new interface for the staking contract at this contracted ID. And again, mind you, this is all kind of just like setting up the environment. All right, so you see here, token one.mint. This is some setup here that we're just minting the user, kind of like pre-funding their wallet to interact with the contract. Assert that the token or the token balance for the user is what we just minted, so 1,000. Here you see initialize, so client.initialize. So when you see the word client, it just means that you're interacting with a staking contract. So client initialize, this could be staking contract.initialize. Here you see the admin token wasm that we're using, and then the token one address. So let's go ahead and dive into this token wasm file or this token wasm function. So you see function install token wasm. It's going to return a bytes value, and what we're doing is importing the Sorbonne token contract that we just kind of have pre-compiled here, and we're going to upload that to the contained simulated blockchain that we're working in from the test environment. But the main thing to focus on here is that we're importing the token file, and we're able to use different functions from this token file thanks to this install token wasm function. So again, this returns a bytes 32 value, and that's what we're going to use within the test. All right, so client.initialize, we're passing in the admin, we're passing in the token wasm value, and then we're passing in the token address, right? We're calling the function start campaign. So this is going to set the is active value to true. And again, we can't make deposits or withdrawals unless that is active value is true. Moving forward, client.deposit. So we're taking in a deposit from a user, which token that they're depositing, and the amount that they are depositing. We're going to say assert that the user contribution of the user that just deposited matches the total deposit that they made, and we're going to assert that the total share token balance of that user matches the initial deposit. That's all they should have right now. And then we're going to go ahead and test the withdrawal function, making sure that the user, after they make the withdrawal, has 0 contributions left within the contract. So again, just as an example, when we run that test, everything is okay, and all of this logic passes the way it should. All right, so that's about it for me. Again, if you want to check out the DeFi contracts portion, or if you want to check out I'll go ahead and go through the links again one more time. So we have the Okashi link here. If you want to check out the set title smart contract in an online IDE kind of environment, that contract should be built out. You should be able to just quickly hit compile, start testing out all of the functions that live there. Again, this setup slide, this QR code here is going to take you to the setup part of the getting started section of the docs. You're just going to run 3 simple commands to get started with the Stellar CLI. If you want to check out some more advanced smart contracts that we just went through, including more advanced, data storage, cross contract calls, as well as some more various examples of getters and setters, you can go ahead and check out this QR code here, which will take you to the consensus hackathon, and you should see a couple of directories, namely staking and data types. All right, so in conclusion, I always tell developers to read the docs, as you can never go wrong with that. Feel free to scan this QR code here, and it will take you right to the stellar.org/developers landing page, where you'll see all of the good developer docs that you will need. And last but not least, once again, my name is Julian Martinez, Senior Developer Advocate here at SDF. It's been an absolute pleasure. I love talking about this stuff. Really love having developer workshops and tutorials. Happy to do them anytime. And I really hope that you guys all learned something today. If you have any questions, then please do hop in the developer Discord or the Stellar Discord in the should be Sorbonne-dev or dev-help. Any one of those channels. In general, just join the Discord, and you can also ping me at the Godhand underscore. Again, that's at the Godhand and then an underscore sign if you have any questions. But yeah, thanks again so much for your time, and I hope to see you all soon. Take care.